Welcome to my tutoring session in chemistry. The current video is part 1 of the 4-part series in thin layer chromatography. In this video, I'll explain the principle involved in the thin layer chromatographic separation and the saturation of the TLC chamber, and with a brief note on stationary phase and mobile phase used in thin layer chromatographic separation technique. What is thin layer chromatography? Now, thin layer chromatography is a separation technique where the given sample mixture is separated into individual components using a solid stationary phase and a mobile phase. Now, a stationary phase, as the name indicates, is a non-moving phase. Generally, it is a solid silica gel or alumina that is used. And mobile phase is a moving phase, is generally a liquid solvent. Now, how do you prepare a stationary phase? Now, stationary phase is prepared using a slurry of silica gel and a glass plate. Now, silica gel slurry is prepared by making a suspension of silica gel powder in a low boiling solvent like chloroform. And this prepared slurry of silica gel in chloroform is applied as a thin layer over the glass plate of suitable dimension. Now, the TLC plate can be prepared in the laboratory as per the procedure mentioned here. But TLC plates are also available commercially, and they are of two types. One is glass backed silica gel plate. Other is aluminum backed silica gel plate. Now, thickness of the layer for analytical plates is around 0.25 millimeters, and for preparatory plates the thickness varies from 0.5 to 1 millimeter with a glass or aluminum backing. Of these two types, it is more convenient to use the aluminum backed TLC plate, as it can be easily cut into a suitable dimension using scissors and can be easily bent or rolled, and that can fit into a TLC chamber. Now, the commercially available TLC aluminum sheets mentions the label as silica gel 60 GF 254. Now, each detail in the label has its own significance. Now, silica gel indicates that the stationary phase is prepared using silica gel. The number 60 indicates the pore diameter of the silica gel particle in angstroms. Letter G indicates the presence of gypsum in the stationary phase. Now, gypsum, chemically it is calcium sulfate. Now, commonly we call it as plaster of Paris, and it enables a strong binding of the stationary phase towards the aluminum support. So, gypsum is a binder. And the letter F indicates the presence of a fluorescent indicator impregnated in the silica gel layer. And the number 254 indicates the wavelength, that is 254 nanometers, at which the fluorescent indicator absorbs the radiation and gives fluorescence. So that's the significance of this particular label. Now, the particle size of silica gel in this commercially available TLC plates is around 10 to 12 micron meters with a pore size of 60 angstroms, and the layer thickness is around 100 micrometers with aluminum support. Now, the principle of separation in case of thin layer chromatography is adsorption. Now, the principle is same both for TLC, that is thin layer chromatography, as well as for column chromatography. But column chromatography differs from TLC in terms of the glass column that is used as a solid support for the silica gel slurry that is filled inside the glass column. So in case of column chromatography, a column of silica gel slurry acts as a stationary phase which is filled inside the glass column. So the glass column acts as a solid support, while in case of TLC plate, the glass plate acts as a solid support over which the thin layer of silica gel slurry is applied of uniform thickness. But the principle of separation is same for both the techniques, that is adsorption. Now there are 4 prerequisites for carrying out the TLC separation. One is the solid support, which could be a glass, polyester sheet or aluminium. So it acts as a solid support over which the stationary phase is applied. Now stationary phase could be silica gel layer or alumina layer. Now over this stationary phase, the sample is applied. Now the sample could be an individual sample or it could be a multi-component mixture. And over this, the mobile phase, it flows through the stationary phase by capillary action. Now the sample is sandwiched between the stationary phase and the mobile phase. And the distance the sample travels over the stationary phase, it depends on the relative affinity of the sample being separated towards the stationary phase. So you draw a baseline at the lower end of the TLC plate, and this baseline is generally around 1 centimeter from the lower end of the TLC plate. Apply the sample over the TLC plate using micropipette, microsyringe or capillary, and the mobile phase, it travels through the stationary phase by capillary action when it is placed in the TLC chamber for development. And the sample travels varying distances, and the distance traveled by the sample component depends on the relative affinity towards the stationary phase. So now the TLC plate is ready for separation. You draw a baseline using pencil at the lower end of the TLC plate, and it should be around 1 centimeter from the lower end of the TLC plate. Apply the sample over the baseline using a micropipette or microsyringe. If micropipette, microsyringe are not available in the laboratory, you can always use the capillary tubes that are very economical, cheaper. Now the glass plate, it acts as a solid support over which a thin layer of silica gel or alumina slurry is applied, which acts as a stationary phase over which sample is applied. And the mobile phase, it moves or travels through the stationary phase by capillary action. Now the sample is sandwiched between the stationary and mobile phase. It travels varying distance over the stationary phase depending on its relative affinity towards the stationary phase. So 4 prerequisites for TLC technique: a solid support, stationary phase, sample applied over the baseline on the stationary phase, and the mobile phase, which travels over the stationary phase by capillary action, and thereby the sample gets separated. Now the mobile phase, it moves or travels to the stationary phase by capillary action, and in the process the sample gets separated, or it moves a particular distance over the stationary phase depending on its relative affinity. Now the principle of separation for thin layer chromatography is adsorption. Adsorption of what? Adsorption of the molecule to be separated over the stationary phase. So the separation of the molecule is based on the adsorption of the molecule on the surface of the solid stationary phase, that is silica gel, which is highly polar in nature. And TLC technique is useful only in the analysis of non-volatile solids or liquids. Now in case if you are trying to separate volatile liquids, by the time you carry out the separation, the sample that you applied over the baseline, it could have evaporated. So TLC technique is employed only for the analysis of non-volatile solids or liquids. So as the solvent ascends the plate, the sample or the molecule is distributed between the moving liquid phase and the stationary solid phase. This is called developing the chromatogram. So before you place the TLC plate for development in the TLC chamber, it is always recommended to saturate the TLC chamber. So saturation of the TLC chamber is a must. So how do you do that? You take a glass chamber, TLC chamber, fill it with the mobile phase used for the separation, and close the TLC chamber. And over a period of time, you will see that the TLC chamber is completely saturated with the vapors of the mobile phase. So now the TLC plate is ready for developing the TLC plates. Now introduce the TLC plates. Now before you introduce the TLC plates, draw a baseline at the lower end of the TLC plate, apply the sample on the baseline, dry the spot, and when you are introducing the TLC plate into the TLC chamber, make sure that the baseline over which the sample is applied is slightly above the level of the mobile phase. So if the baseline is submerged in the mobile phase, the sample that was applied on the baseline will be washed away and there will be no separation. So make sure that the baseline over which the sample is applied is always slightly above the level of the mobile phase. Now close the TLC chamber, and during the development you'll find that the mobile phase, it moves or travels through the stationary phase by capillary action, and in the process the sample that is sandwiched between the stationary phase and the mobile phase, it gets separated. It moves varying distance depending on its relative affinity towards the stationary phase. Now with saturation of the TLC chamber, you will always end up with good separation. When you don't carry out the saturation, so in case you are carrying out the separation without doing the saturation of the TLC chamber, you will end up with an edge effect. You will end up with a bad separation. So what is this edge effect that happens when you don't saturate the TLC chamber? Now during edge effect that is caused when the chamber is not saturated, you will find that the solvent front at the center has traveled faster than the solvent at the edges. So during edge effect, you will find that the solvent at the center has traveled faster than the solvent at the edges. So when this happens, the path which the components travel will vary. The components will travel either towards the left side or right side. So its motion or movement is deviated from its defined path, and thereby the components will travel a lesser distance due to edge effect, and it will travel a lesser distance, and that is going to affect the RF values. So RF values will be lesser than what is actually the RF value of the compound with saturation. So it is always recommended to saturate the chamber, and this is to avoid the edge effect. Now coming to the selection of the mobile phase. That is the solvent system. Now the solvent or the mobile phase selection is purely based on experience. So with experience, you learn how to select the solvent system for a particular separation. And this you can learn by trial and error method. And the solvent or mobile phase selection, it depends on three factors. Nature of the substance to be separated. That is, the substance could be polar, non-polar, or of intermediate polarity. It also depends on the nature of the stationary phase. The stationary phase could be polar or non-polar. And the modes of chromatography separation: normal phase or reverse phase. In normal phase chromatographic technique, the stationary phase is polar, while in case of reverse phase chromatographic technique, the stationary phase is non-polar. So when the sample is polar in nature, you always opt for a polar stationary phase, and a mobile phase should also be polar. And when the sample is non-polar in nature, you opt for a non-polar mobile phase. So the separation is based on distribution of the sample being separated between the stationary phase and the mobile phase. So the given sample mixture is separated into individual components by using stationary phase and mobile phase, and the components being separated, they travel varying distance over the stationary phase, and the distance traveled by the components depends on its relative affinity towards the stationary phase. So here the component G, it has traveled a distance x1, component A has traveled distance x2, component T traveled distance x3, and sample P has traveled distance x4. So when you're calculating the RF value, and when you're trying to measure the distance traveled by the component from the baseline, always consider the center of the component that is being separated. So consider the center of the spot when you're measuring the distance from the baseline. Now let's say we are given a sample mixture for separating by adopting TLC technique. Now sample mixture is abbreviated as S, glycine sample as G, alanine as A, tyrosine as T, and the component phenylalanine as P. Now the concentration of the prepared sample solution is normally around 1%. Take a TLC plate, cut into required dimension, draw a baseline at the lower end of the TLC plate, and make sure the baseline is around 1 to 2 centimeters from the lower end of the plate. And I will always recommend to draw a reference line at the upper end of the plate for the beginners in TLC, and this will be around 0.5 to 1 centimeter from the upper end of the TLC plate. The reason is you should know when to stop the separation. When you place the TLC plate in the TLC chamber, the mobile phase will move through the stationary phase by capillary action, and when it reaches the reference line drawn for the solvent front, you can stop the separation and remove the TLC plate. So this is recommended only for the beginners. Now apply the sample mixture over the baseline and make sure the diameter of the applied spot is around 2 to 3 millimeters. It should not exceed 2 millimeters. And what about the volume of solution applied? It should be somewhere around 2 to 5 microliters with concentration of 1%. And the sample solution is generally prepared using solvents like chloroform, dichloromethane, and acetone, as these solvents not only solubilize the sample but also it is highly volatile. The moment you apply it, it will evaporate, leaving only the sample on the baseline. So how do you apply the sample mixture over the baseline? You can always make use of micro syringes, micro pipettes, and even capillaries can also be used for applying the sample over the baseline. So in case micro syringe or micro pipettes are not available in the laboratory, you can always use the cheaper capillary tubes. Never use droppers, because when you use droppers to apply the sample over the baseline, you cannot control the addition. It's every possibility that you may add excess of the sample solution over the baseline. So the given sample mixture is separated into individual components, and it travels varying distance over the stationary phase, and the distance traveled by the components depends on its relative affinity towards the stationary phase. And the mobile phase, it moves or travels through the stationary phase by capillary action, and it is moving against the gravity, and therefore the separation process is a bit slower. And when the solvent front has reached the reference line that is drawn for the solvent front, stop the separation process, remove the TLC plate from the chamber, dry the plate, and then you can measure the distance covered by the solvent front. Say, y is the distance traveled by the solvent from the baseline. It could be, let's say it is 5 centimeter. X1 is the distance traveled by glycine. X2 is the distance traveled by alanine. X3 is the distance traveled by tyrosine. And X4 is the distance traveled by amino acid phenylalanine. And when you're trying to measure the distance traveled by the component from the baseline, always consider the center of the spot from the baseline. Now here, of all the 4 components, the component glycine, it has traveled a shorter distance because of its greater affinity towards the stationary phase, as it is highly polar in nature. While phenylalanine, represented by P, it has traveled a longer distance because of its lesser affinity towards the stationary phase, and is highly non-polar in nature. Now stationary phase here is silica gel with polar selenol groups, where you find the polar hydroxy group covalently bonded to silicon, and the mobile phase used is butanol acetic acid mixture. Now butanol acetic acid mixture is a recommended salt system for separating amino acids. And how do you calculate the RF value? By dividing the distance traveled by the component from the baseline by the distance traveled by the solvent from the baseline. So for glycine, it will be 1 by 5. So 1 centimeter is the distance traveled by the glycine from the baseline, and 5 centimeter is the distance traveled by solvent from the baseline. So 1 by 5 gives 0.2. So 0.2 is the RF value for glycine. And likewise, you can calculate the RF values for other amino acids. Now the RF value is a constant value for a given combination of stationary and mobile phase. As you vary the polarity of the mobile phase, the RF value will also vary. So RF value is a constant value and it's a fixed value for a given combination of stationary and mobile phase. So amino acids travel at different rates up the silica gel layer due to their different affinities towards the stationary phase. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.